Today we will see the next practical, that is practical number 5, which is based on the matrix method of the 2D beam elements. So as shown on the screen, this is the numerical which is taken from practical number 5 of case number 6, in which having the length of AB is considered as 6 meter. So by default, as the load is acting at the center, so L by 2 is given. So therefore total span is equal to A, B and C is there. Okay, so 6 meter is considered here. So here in second case for BC it is considered as 7 meters, that is 3.5 is already given. Okay, here the factor is considered as I for AB and for 1.5 for BC. So first of all we will see the manual calculations of the same method. Okay, so here we have to define the degree of kinematic indeterminacy. So here the two unknown is there, B and C. So we have to start marking the unknown from 1 here, 2 here, then 3, 4, 5 and 6. Okay, 3, 4, 5, 6 are known, whereas 1 and 2 we have to calculate as a degree of kinematic indeterminacy. Okay, so d over ki will be equal to number of unknown is 2. Now the equations for the span of AB will be equal to stiffness matrix for a structural matrix SM1, okay, or AB. You can see that the formula is like this. Okay, 12 by L cube 6 by L square. EI will be taken as constant outside. Then here the coordinate will be acting 3, 4, 1, 5. Length is 6 meter. EI is considered as I. So when we put this value in your equations in the matrix, you will get the answer like this. Okay, and the coordinates is 4, 3, 5, 1. Then second is SM2 matrix. So SM2 matrix, the equation is like 5, 1, 6, 2. Equation is 5, 1, 6, 2. The coordinate is 5, 1, 6, 2, and you have to take EI as constant outside, and you will get the answer like this when you multiply this value inside the bracket. Okay, then the formation of the global load matrix K will be equal to 2 by 2, and the coordinate is 1, 2, 1, 2. Okay, then the global load matrix AC, you have to consider action to the member due to the load AML1. So we have to split this two diagram into two parts. Okay, 25, 30 kilonewton is there. Then we have to calculate the fixed end moment. Okay, as the load is acting, WL by 8. Here also WL by 8, the formula will be available. Okay, you have to put the value and you will get the answer like this. Okay, then you have to calculate the reactions first. Okay, summation of moment about A equal to 0, you will get the answer of RB and RA. Then similarly RC and RB. Okay, then after this you have to calculate the AML, that is equal to 12.5. We have to take the coordinate as 12.5, this 12.5. First we have to consider then 18.75, then second equal to 18.75, then 12.5 and minus 18. This is AML1, then this is AML2, 15, 26.5, 15 and minus 26. So these are the two AML1. Okay, coordinate we have calculated for the respective span. Then action in the joint due to the load AE will be equal to, okay, 1, 2, 3, 4, 5, 6. Okay, so AFC and ALG value we have to consider. So these two coordinates we have to consider, 1 and 2. Okay, this will not applicable. We have to consider this value 7.5, minus 7.5 and 26.25. So we have to see that where 1 is formed. So 1 is formed at this point. Okay, here. So we have to add this value and we will get the answer as minus 7.5 and 26.5. Then the displacement matrix. Okay, K into DM is equal to AFC. So 1.5. Okay, K matrix you have to write. Then you have to write the unknown displacement matrix. Then AFC minus 7.5 and 26.5. By solving the simultaneous equation using calculator, you will get the answer as DF1 and DF2. Then final member forces is like this. Okay, AML1, AML plus SM into DM. This process you know better. Okay, we have already solved n number of numerical. Okay, when we cover our theory part. Okay, so you just go through that and you have to solve this numerical like the same. Okay, and you will get the answer like this, and then finally we will get the answer and we will get the final forces like this: 13.8, okay, and 29.8 and 37.52.5. Now let us see that how to calculate the same forces by using StatPro. Okay, so let us see that. You just have to minimize this. Okay, just go to the stat output file, stat file. Okay, here what you have to do, uh, here go to the new project, go to the space frame, name the structure as P5, as practical number 5 is going to be conducted. Then here under practical 5 you have to go, then next add beam, okay, like this, and then the window appears like this of a grid form. So let us wait. So window will appear like this, okay. Go to the create, go to named it as A XY, okay, then okay, then go to the define path, okay. Here you can click your cursor here, okay. Then the first dimension is total 6 meter, you can go for 6 meter. Then the next dimension is your 7 meter, but here 7 meter is not mentioned, so you just skip, give the command escape here, then go to the translation repeat, okay. Before translation repeat, go to the node cursor, select the respective intermediate node, then go to the translation repeat. X coordinate is there, we have to define the spacing as 7 meter, okay. Number of step is 1, link the step and then okay. So here we will get the answer like this, okay. Then take the view as a front view, okay. Now we have to define the member property first, okay. So first of all select the corner node first, go to the command support specification, add it as in diagram itself, it is a fix, so assign as a fix, assign and close. Now next two part is that is a hinge support. So go to the command, go to the support specification, then go to the pin. Here it is given as pin, assign as a pin, assign and close. So if you see the difference, the fixed symbol is like this, okay, in appears in your STAD, whereas the pin support is appears like this, okay. Then the next is that what you have to do, you have to define the members property. So as we know that the members property for AB span the I value is I, for BC span the I value is 1.5. so we have to define the members property separately. First of all select the member AB, then go to the command, go to the members property, then prismatic, then rectangular section you have to go to rectangular section, then YD you have to define as YD is the depth required, so it is I, consider as 0.45, ZD is 0.23, then assign, then close, okay. Again select the second member BC, command, go to the member property, prismatic, then go to rectangular section, but here it is a 1.5i, so therefore as the factor is 1.5, therefore the depth factor will change, so it will be 515, okay, 51, and ZD is equal to 0.23, okay. Then assign, close. So if you see that two members property will be defined, go to the labels, okay, and go to none, apply and okay. Now next step is to assign the external loading, okay. So go to the general, here load and definition is there, go to the load case, define add, then in under none go to the live load, the name the title as live load LL, add and close. Go to the live load properties, then under this add this and go to the member property, go to the concentrated force. The first load acting is first load which is acting is total is 25 kilonewton, okay. So go to the concentrated go to the member force, go to the concentrated force that defined as minus 0.20 to 25 kilonewton, the distance is 3 meter, okay. Add it here, close. Again go to the live load, then add, go to the live load, okay. Before defining this, okay, first of all select this, assign to selected member, okay, like this, okay. Then again go to the add property. Okay, under this member load you have to go to, and then concentrated load. Then the second value is 30. So write it as minus 30. The distance is 3.5. Okay, then go to add and close. Then select the respective member. Okay, select the respective loads. Okay, and then assign beam, and okay, like this. Select all the structure. Okay, then go to the command, go to the analysis, perform analysis, all. Okay, analysis, run analysis, save, like this. So after this you will get the answer. If you see that the window will appears like 0 error and 0 warning. Okay, then go to done, post processing, live load is there, select the live load. Okay, and apply. Okay, so maximize this screen. By default it is given as it is a deflection mode, so we require the bending mode. So click on the MZ. Okay, then click the control and scroll the mouse. You will get the final shape of the bending moment. Then how to get the final values? Go to result section, values, bending values, and mid bending and midpoint you have to select, then annotate. Okay, so by this way you will get the answer like this: 13.54 and 29.2. So this is the answer you will get. Similarly, if you see our manual calculation also, the answer is 29.3 and 13.4. So by this way you can compare your manual calculations with your STAT output. Okay, so you have to solve this numerical manually, and you have to calculate the same values by using STAT, and compare the shear force and bending moment in a separate table. Okay, so solve the practical number 5. Okay, in all respect, and complete it and submit it on or before 26th. Thank you.